Now your spectrometer is going to typically cost many hundreds or thousands of dollars. And all the pieces that are inside of it are typically going to be things you just bought as a set in this existing instrument. However, there's one piece that you're almost always going to be choosing on a day-to-day basis, and that's going to be your cuvette. This is your sample holder. Now there's two big aspects of choosing a cuvette that you'll use. There's going to be the material it's made from, and there's going to be the construction of it, the shape of it. Because both those things are going to give you different opportunities. So let's take a look at some examples. If we're doing visible spectroscopy, we're going to have the most options as far as our materials go. Basically, if it's transparent, we can use it. And we can tell what's transparent with a quick glance with our eyes. We know what we can see through. So optical glass, quartz, plastic, all of these are going to be good options in the visible range. Now the big thing you want to think about is, will my compound start to stick to any of these things? Which ones of these are cost effective? Which ones are durable? Which one do I have? Those are all going to be considerations you have to make when it comes to cuvette. Now, in routine daily work, when we can do it, we often try to work with these plastic cuvettes. They actually are better quality than you expect. You can have them made with really good precision thickness so that they don't have any ripple sort of effect. You know, when you look through clear plastic, you usually see a bit of a ripple. But with a really high quality piece of plexiglass, for example, it actually has a very uniform makeup. And you don't see any of those ripples. Well, they have even higher quality ones for cuvettes. There's also some crude ones, and they don't always matter that it's crude as long as you don't care too much about the decimal places in your measurement. Optical glass is a good choice as well, and is reasonably cost effective. Not as cheap as plastic, but fairly cheap. Quartz, these get more and more expensive. I mean, they are cutting and polishing a piece of quartz, usually artificially made, but still, they tend to be a bit more fragile, and they tend to be a lot more expensive. Plastic, we're looking at maybe $1 a piece. Optical glass, you're probably looking at about $50 for a standard cuvette, and quartz, you're typically going to be starting out in the right around $100 mark per cuvette. Now when we get into the ultraviolet, optical glass will work on the top of the ultraviolet range. In other words, right there in the near UV. So what we'll often do is we'll use optical glass for visible and still be able to see just a little bit of ultraviolet. But if you're going to be doing much work in the ultraviolet, you need to be using quartz. Now this is good for most of the routine work we do in ultraviolet, but if you want to go deep UV, we're talking down to like 100 nanometers, now you've got to have some very specific specialty types of quartz, because you're now getting to high enough energies that you're going to have to start worrying about promoting electrons on just on ions and ionically bound substances. So the crystal lattice itself is something you can start having to worry about promoting electrons out of, and so you have to have some really picky stuff. Otherwise, it's going to start absorbing, and then eventually you'll have the electrons kicking loose. Now, when you get into the infrared, if you're staying in the near infrared, that's right here butting up against the visible range, most of these will still work, probably not the plastics anymore, but you can still get away with quartz and optical glass, probably out till 6, maybe even 700 nanometers, and possibly beyond that. It just really depends on how far out you want to go. But when you actually are trying to do deeper IR work, the kind of thing that you did in organic chemistry, now you need to start using these salt plates, because the salt plates don't end up actually absorbing any of the ultraviolet light. So you use sodium chloride or KBr. You can actually just have a nicely polished disc where you wedge this between them. You can actually make a mol, so you take some oil, you kind of put your substance into that oil, even if it's still a crystal. In fact, it probably is a crystal. And then you grind the two discs together, makes a pretty uniform profile. You stick that in the spectrometer, and that acts as your cuvette. You can also take powders, grind that into the salt powder, press the salt pellet very tightly to make a reasonably transparent window out of the salt. And for that, you'll be using usually a hydraulic press. You'll get what looks like a little frosted piece of glass out of it. You can't see through it, but it's okay because you can't see in the visible through it. In the infrared, the light goes through well enough, and you can get decent quality measurements. So those are the materials you'll typically use in IR. Now let's stay focused in the visible, near IR, and near UV. and take a look at some commonly used cuvette types so that we have an idea of the shape and function that we can get for different ones and some of the use for different forms. Now our most common cuvette is going to be a 1 centimeter path length. 1 centimeter ends up being just about right to do our normal concentration ranges and still get a good enough absorbance reading that we can do some quantitation with it. Now that's because the molar absorptivity for most molecules most of the time is going to be in the hundreds to low thousands range. And remember, that's epsilon. And so if we just think through that, here, I'll actually make that narrow. Absorbance equals epsilon times path length times concentration. We're saying this is going to be 1 centimeter, typically. We'll take a look at this in just a second. We said our concentrations, we're going to want them to be 0.01 at the top end, and probably lower. And we want our absorbance to usually be somewhere in the 0.1 to 0.9 range, I'd say. I mean, we're going to get a lot more specific than that soon, but this gives us a range idea. So, you can see that for that we're going to need this to be, let's see, 100 would give us the number 1. So, that kind of gives you a ballpark of where we're looking at over here. So if we had 1,000 as our molar absorptivity, we'd end up having absorbance of 10, which would actually be really on the high side. Of course, this was really on the high side too for our concentration. Now, realistically, our concentration is probably going to go down to 0.00001, something like that. So 1 times 10 to the negative 5. So if we're all the way down at that point, now let's go ahead and see what happens. Let's slide the decimal 3 places, 2, 3. So we're going to be at 0.010 absorbance units. So we're going to be in the small end there. So you can see that with the common range of concentrations we want to work with, and a common range of molar absorptivities, to get an absorbance that actually gives us meaningful numbers off of the display, it turns out that 1 centimeter ends up being the sweet spot. Okay, so this is our standard version. Well then, what sort of experimental times are we going to want something different? Alright, so let's just think this through. We know that 1 cubic centimeter is 1 milliliter. And just kind of glancing at this, you probably get the idea right away. This is going to be a little bit more than 3 centimeters tall. After all, this is 1 centimeter. 1, 2, 3, yeah, probably like 3.5 or so. Exact numbers depend. Oh, and I should mention our 1 centimeter is the inside diameter there. We don't care about the wall thickness usually. Alright, so we're talking about 3.5, 4 milliliters, something like that would fit in there. Now, keep in mind though, the light from our spectrometer is probably going to be going through right about here. So we need at least 1.5 milliliters to actually immerse to that spot. And if we're worrying about any bubbles from us filling it up, sitting right here along the meniscus, we probably want to fill it up a little bit more. So now we're probably getting close to 1.5 or 2 milliliters. And sometimes that gets expensive. So if you've got an expensive substance and you don't want to have to worry about spending that much money just filling up your cuvette, you just thicken up the walls. You get it so that the beam is still going to be centered up real nice. You only have to fill it to about there. Now you may only be using microliters. Probably hundreds of microliters, but still, it gets you a much kinder price tag on that. Alright, that works fine. But what happens if you have something that's really absorbent or something that's really not very absorbent? 1 centimeter may not be our sweet spot anymore. What if we have a really high concentration or a really dark absorbing molecule, like a dye? Well then, we can just shrink down our path length. We can do a 5 millimeter path length, or we can shrink it down and have a 1 millimeter path length. What if we have something that's fairly dilute, and we still want to do a good quantitation, but we don't want to have to risk evaporating off or thermally damaging the substance? Well, fine. Just increase the path length. There's cuvettes out there that'll do all of these things. I will start pointing out, though, with micro and these, the moment you start changing from that standard square 1 centimeter path length cuvette, price tags start jumping up. What if you actually want to be flowing solutions through or doing thermal control? Well, just cuvettes for that as well. Well, why would you want to do flow? Well, maybe you're doing a reaction. And it's a time-based reaction, and so you're constantly flowing some of the solution out of your reaction vessel through it and monitoring the change in concentration. That'd be one reason. Uh, Looking at kinetics of things. Or suppose that you've got some sort of an instrument and you're trying to separate things out like a chromatography column would have done. If you remember back from doing chromatography columns back in organic or maybe even Chem 2, just imagine that you had one of these with a tube in and then just a tube out to the garbage. It's flowing in here. You're constantly seeing fresh solution in here. And you'd be able to see, hey, look, there's my blue peak. Hey, look, there's the infrared absorbing peak that is invisible to my naked eye. All those little things can start helping you out for doing these measurements on flowing solutions. And some things we actually want to do temperature controls for as well. And for that we can flow water through this front side, through the outside. If you look very closely, there's a little channel right here, here, and all the way up to here. Basically what you've got is a cuvette suspended in a second cuvette. You flow water through to keep it the temperature you want. You pop this cork off, or stopper really, fill up your inner cuvette with the one you care about, and you pass your light just through that inner cuvette. Notice we're going to be going through like this. It's not going through the water jacket at all. So that would be one of our thermal cells. Now for these cylindrical cuvettes, remember, not every solution that we're going to do spectroscopy on is going to be a liquid. Often we're going to have gases. So you can see here that we can fill up gas into this and do our measurement for it. It tends to have a longer path length. It tends to have a good amount of volume to it. And we can have it really a long path length on some of these. I've actually seen cylindrical cuvettes that got up to about 1 meter long. Those things are going to be very exotic and expensive pieces of equipment. But yeah, you could use that for doing long path length measurements of gases. So there's a couple of different kinds of cuvettes that we have there.